All right, folks, it's 9:01. I'm just doing a bit of attendance here, but let's talk briefly about this question. A city with a population of 43,000 had an unemployment rate of 7%. When the population of the city rose to 46,000, it had an unemployment rate of 5.5%. If this trend continues, what will the unemployment rate be when the city reaches a population of 50,000? So I want you to think about how we have 2 points, really. They're just in kind of weird, like we have 1 point, one coordinate that's really big, and then another one that's really quite small. But you can turn that into a coordinate, something comma something else. And then from there, it's very typical. We've done this kind of work before where maybe we will find our slope using our slope formula, and then we can use either equation to either form, either the slope-intercept form or the slope point form to find an equation for it. So spend a few more minutes on this, and then we'll get started with today's class. All right, folks, is there anyone else that do you need a bit more time on this question here? How are we doing? Bit more time? Feeling okay? Feeling okay? All right. Let me check in with you guys. How are you doing today? Did you have a good weekend? Does anyone?
I got my braces off, so.
Let's see. Yeah. Wow. Congratulations, Krista. How does it feel?
It feels normal, but my teeth feel like super polished. So
okay.
I have a lot of a lisp right now, which works really well.
Is it just?
I like to talk a lot, so then all my siblings are like, Krista's got a lisp.
I guess it's just like your mouth has to get used to not having braces again.
All of the siblings.
And it's because I have a retainer, so.
Oh, okay. I see. Yeah. So is that like a retainer that's in there all the time, or like? Mm-hmm. Yeah. Okay.
I have to wear it all the time for the first year, and then after that, just nights. So.
Got it. Yeah. Okay. Well, congratulations. Nice. That was your weekend activity, getting your braces off. Does it take long? How long does it take to get your braces off?
It took like maybe 45 minutes at the most because they had to like polish out the glue.
Okay.
It's pretty quick.
Yeah. Okay, cool. Anyone else, anything they want to report about their weekend? What'd you get up to? I visited my sister and brother-in-law in Vancouver, which was really nice. Hadn't seen them in just a little while, so it was really nice to spend some time with them. Yeah, we played a few board games and just kind of hung out, took it easy, and then came back. Oh, excuse me.
I went up to Nanaimo and then over to Courtney. Mm-hmm. And I went to the Valley Village there, and I found a really good condition suit, almost my size, so I can tailor it for grad. So got that for like $34 instead of the $400 suit I thought I was going to have to get.
Sweet.
Yeah.
Saving some money.
Exactly.
He was in Courtney getting stuff and hanging out with friends. I worked at a demolition job site.
Oh, okay. How was that?
Yeah.
Have you done that before?
Yeah, so it's not really like the demolition side of things. We're doing all the hazmat because it's a really old house. It's got like lead paint and asbestos.
Yeah.
So we were pulling out, I cut myself a few times ripping out the furnace.
Yeah.
Because it had asbestos fire blanket inside that couldn't be there because just in case for when the demolition team comes in, it has to be fully safe.
Oh, I see. Okay.
Yeah, so we were ripping out all the unsafe stuff.
So this is before it's getting demolished. You go in and you take out as much as you can that could be like asbestos or like lead paint and stuff like that?
Yeah, so pretty much we strip it down to where it's just the frame of the house, pretty much.
Oh, okay.
And there's like shelves and stuff inside.
Yeah.
But all the siding had to come off because it was all lead paint.
Yeah.
And so we had to basically strip the house down to nothing, pull out all the insulation, a bunch of painted walls because it all had lead paint.
Yeah.
And then it's just basically the frame of the house is left, and then the excavator's going to come and just knock that down.
Got it. Do you have to wear like a mask and stuff when you're doing that?
You have to wear at least a mask and gloves for it to be legal. So that's what we did. We wore mask and gloves.
Got it. Cool. Wow. Maybe a kind of a neat job anyway, like cool to see some of the stuff that, how maybe construction has changed and that kind of thing. Anyone else? No. All right. Let me know if you do have something you want to share. I like hearing from you guys. I like it. It can be kind of, you know, meeting online like this. It can be kind of tougher to connect in the same way as if we were meeting in person. But you know, that's why sometimes I ask you about your weekend and things like that. I want to learn a little bit. All right, so we did this. Just a reminder that that on Friday you will have a Chapter 5 test open. Okay, Chapter 5 test on Friday, and it will be open for a week. I have not built it yet. And will be all about like linear equations and that kind of thing. Also, I was talking with a colleague of mine, and we're just trying to figure out some ways that we can make sure that you guys are still like learning what you need to be learning, that kind of thing. But maybe having like, as it is, basically every class, you get a challenge question and a homework assignment, and then sometimes one other thing, right? And so adding all that up, it's just a lot of things that you've got to submit. So we're trying to think of ways that we could maybe reduce that down. And if you do have any ideas, and you know, like an idea like, oh, get rid of homework, well, that means that it hurts your learning, right? So, but yeah, if you do have any ideas, let me know kind of near the end of class today. Any ideas of making sure that learning is taking place, but so that you just have less things that you have to hand in. All right, today, function notation, our key ideas, function notation. Have we talked about it in class before? Does this name sound familiar? Function notation. Does it, Rachel, is that a nod? Yeah, okay, all right, good. I think we have talked about it in class a little bit. Yeah, Raquel, does it sound familiar? Function notation a little bit? Okay, all right. We'll talk about it more today and use it more today. Function notation is a very commonly used way of writing functions. It allows us to clearly communicate. So that's one of the main things, is that it makes things clear when we're communicating. And it is very useful in Desmos and other applications. It's very, very common. Okay. In addition to that, we're going to talk a little bit about calculus today, just because it kind of worked out in one of the examples. So I'll give you a bit of an intro lesson for what calculus is. Okay, so a very straightforward first example. We know a function can be written using x and y. So we've got our x and our y here. Y, one of them is independent and one of them is dependent. Which one is which? One is independent and one is dependent. You remember? Come on. Come on. Come on.
Is it the +5?
The +5, that would be like the y-intercept. That's kind of what the 5 represents, right? But between x and y, so our +5 would be representing, hey, we're intercepting the y-axis right there. But between the y and the x variables, one of them is independent and one of them is dependent. All right, so I'll tell you. The x is the one that's like the input, right? The input, it's kind of, it can stand on its own, right? And so it is the independent. Input independent, okay? Whereas a y, the y value depends on what the x value is. So this is our dependent, typically, okay? And of course, depending on the equation, they change them, they use other variables. They can use c, we've seen c for cost, we've seen n for number, that kind of thing. That same function, all right, so this, this function here can be written using function notation, and it looks like this. And we can see that the 2x plus 5 is the same, but what has changed is that the y has turned into this thing that we read as f of x. All right, f of x. Repeat after me, please. Répétez, s'il vous plaît. Repeat after me. F of x.
F of x.
Okay, good. Thank you, Ruben. Maybe others repeated with their mics muted, but yeah, f of x. All right. So so the benefits of this, right? We've kind of got this thing, and I sometimes use an analogy of like f of x then is kind of like a briefcase, right? Imagine that I have a briefcase and it says f of x on the side, and I can put things in that briefcase, like that briefcase becomes a holder for something else, for a function, for doing something, all right? So benefits include the ability to name functions. So this one has a name. It's no longer just a stray function that you see on the street, right? This function has been adopted, and we've given it the beautiful name f, right? So this function is named f. F is the most typical one because f stands for function. So this one is called f. Very commonly you see g of x as well, and you guessed it, you see h of x as well. But of course, if we have something that's like talking about cost, we might have c of x. Okay, stuff like that. All right, so that's a benefit. We can also clearly state what the input is. So for example, here we see when we have f of x, we're saying that the input is this variable x. So, you know, like this, maybe this happens sometimes, but sometimes we have something like this, y equals 2x plus b, because we're not quite done this equation. And maybe it's not clear to us, hey, is the b the independent variable or is the x the independent variable? Whereas if we had stated, so it's ambiguous, we don't know for sure. If we had stated that we had this function f of x equals that, we can clearly see that, okay, the x is an independent variable. We've got to find out what b is before this thing is done. Okay, so we can clearly see that. And we have the ability to plug in numbers and more. For example, find f of 9. So let's try this just with this function here. We've got f of x equals 2x plus 5, right? And if I'm trying to find f of 9, I want you to realize what we did here. We took this, this thing that I'm going to highlight in yellow. We took this independent variable x, and we replaced it with the value 9. And so that means that when we write the rest of our equation, whenever I encounter x instead, I am replacing it with 9. It kind of makes logical sense. Okay, I replaced x with 9 here. That means I'm going to do it here and here too, right? And so we can solve this. We get 18 plus 5, or 23. All right. We can also do something like this. This seems weird, but check it out. Okay, we can also find f of 3x, for example. Actually, let me just change that to we can do that, but I'm going to change it. Let's say we were finding f of 3a. All right, this is interesting because this we're replacing x with 3a now instead. So my 2 gets written out like normal, but that 3a is what replaces the x. All right. And when we multiply this out, we end up with 6a plus 5. Now this we can't solve anymore. We can't replace that a. We don't have enough information. But what we've done is we've found f of 3a. F of 3a. So we're done. So yeah, we can kind of illustrate that stuff here. Questions at this point? Questions on this Monday morning? Happy Monday morning, by the way. I hope you're doing well. Do you have any questions? Right. If there are no questions, I've got my eye on chat too. If you have any questions, you can put them in there. Did you know that? Did you know that there's a chat function in Zoom? Okay, so here's another quick example. Given f of x equals 3x plus 5, find f of 2. Okay, so just to illustrate one more time, what am I gonna do? What am I gonna do is write that function out one more time. And I am finding f of something, right? And notice all I've done is I've taken x's, the x there, I know I'm gonna replace it with something. In fact, I am replacing it with whatever I put right there. I'm replacing it with a 2. So I go ahead and do 3 times 2 is 6, 6 plus 5 equals 11. Okay, great, straightforward math. I just wanna show you how you can do this stuff in Desmos to great effect, all right? So if we open up Desmos, Desmos understands function notation very well. If I type in here 3x plus 5, so the answer was 11, I can type in there f of 2. Look at that, f of 2, and it spits it out. It tells me my answer right there. Right? Kind of nice. I can even do something like f of a million, no, 1, 2, 3, there's a million. F of a million. How about 1,000,002? No problem, right? So Desmos does the calculations very quickly. It understands.
Not to be rude, that's 100,000.
Hey, that's not rude. Thank you for the correction. Okay, how about 1,000,002? There we go. So yeah, we got we see that Desmos can do that kind of stuff very quickly. Actually, I wonder if Desmos can do f of 2x. It graphs it. Okay, that's very great. So so f of 2x we realize would become a new function, right? If we actually, I should rename it something else. Oh no, that's okay. If I try to find f of 2x, well, I know I'm gonna do this, right? I'm replacing x with 2x, end up with 6x plus 5. And that's what we've got there, right? We've got this purple line, which is now twice as steep because I've replaced an x with a 2x. Very interesting. Thank you, Desmos. All right. We can also do something like this. Stop me if you have any questions or corrections, like when I can't count how many zeros are in a number. Given f of x equals 3x plus 5, solve x for f of x equals -7. I just want to illustrate that this is similar to what we've done before, where we are given a y value. We're told that y equals -7. We're basically solving this. I just want you to get used to, hey, we've got f of x equals -7. So let's see. We've got f of x equals 3x plus 5. There's a couple of ways to think about this. what I usually do is I think, okay, right here, I'm told that f of x is -7. That means that here, where I see that f of x, I'm going to replace it with a -7, and I copy out the rest of the equation. Right? And then I just solve for x here. So bring that over there. That's -12 equals 3x, right? What I did is I brought that -5 over. And then I divide by 3. Divide by 3. Divide by 3. And I get x equals -4. All right. We've got this note, try it in Desmos. So I'm gonna just head back to where we had that Desmos graph. We've got this answer of -4. How can I do that, folks? I wanted to know f of x equals -7. How can I use Desmos or graphing software to help me find that? Whenever we've got something like this, f of x equals -7, or if instead it was y equals -7, I want you to realize that what we can do is we can, do a quick, straightforward function. Y equals -7. Actually, yeah, which that does a trick. We get this black line here. Let me just rename or recolor it so it doesn't blend in so much purple. Okay, we've got this purple line here, and they intersect right there, -4 with an x value of -4. This is basically saying, hey, when is this red line? When is this function f of x equal to -7? Well, it's at exactly this point when x is -4. All right. So we can solve it that way too. We can solve it algebraically or graphically. Last chance for questions all year. Okay, this is it. This is your very last chance for a question. Okay, that's it. No more questions the rest of the year. Just joking. Here we go. We have another example we're going to look at. Determine the slope-intercept function, which is, f of x equals mx plus b. If f of 1 equals 4 and f of 3 equals -2. All right. Folks, how can I turn these two things into points? This is very similar to work we've done like last class and the class before, where we're coming up with a function, but we have now, instead of like a word problem that's telling us a point, we have function notation. So how can I turn this into a point, and how can I turn this into a point? I need someone to tell me. What do you think? How can I turn f of 1 equals 4 into a point? All right, folks, well, look at this, right? What coordinate would this 1 be? Like we've got two numbers here. We've got a 1 and a 4. We know that they're related somehow. This one is actually our x coordinate, right? If we remember, f of x equals our function. Well, f of x, if we say that we have f of 1, what we've done is we've replaced x with 1. So 1 is our x coordinate. Furthermore, we've said that f of x we've said that f of something equals 4. So our f of something, this kind of represents our y-intercept, and so that becomes our value 4. Okay, so what would my coordinate be over here for the blue one?
3 and -2.
Mm-hmm. Yeah, okay, so we can kind of follow the same pattern there. And then from here, this is very familiar, right? We can use our slope formula, y2 minus y1 over x2 minus x1. We get, I'll call this 0.2 and this 0.1. So we've got -2 minus 4 over 3 minus 1. That's -6 over 2 or -3. That is my slope. I like to use my slope intercept slope point form. And let's plug in what we know. So I'll use this, I'll use that red point. Of course, again, our y coordinate is that value 4, right? And we've got a slope of -3, x minus 1. Okay, so still very similar to what we've done before, just kind of starting off a little differently, where we have to interpret this f of 1 equals 4. All right. Distribute y minus 4 equals -3x plus 3. And then add 4 to each side to cancel it out over here. Plus 4, plus 4. We've got to do this step here because it's asking for a slope-intercept function. Y equals -3x plus 7. Okay, and this is done except that it asks for it in function notation. So all I have to do is replace y with f of x, right? I'm just using that notation instead of the y variable. Done. All right. Questions about that? All right, folks, we're going to take a break. Let's set a timer for 8.3 minutes, around 8 minutes. That's a nice break. I feel like I appreciate that. So we'll be back in 8 minutes and 14 seconds. Folks, we're gonna move on here. We've got another example here. I'm gonna walk through both of these, and then I think I'm gonna introduce to you just two, it won't take long, but two quick questions that I'll ask you folks to work on in a breakout room, and then we'll come back. That will be brief. That will be like 5 minutes max. So don't go into your breakout rooms and like chit chat and like find pictures of Homer Simpson or whatever, you know. Drayden, I'm looking at you. Actually, I don't think you've ever put a picture of Homer. Maybe you have. Homer Simpson?
Nope.
No, okay.
I don't have any pictures of him.
Just
Okay.
this freaking bunny thing. We don't.
Oh yeah, the bunny. All right. So folks, in this one here, look at what's going on. We've got f of x equals 2x plus 1. And our first question here says, what is f of 3x? And so I want you to realize what we're doing is we're replacing this x with this 3x. Easy, easy peasy. So I'm going to start by writing out the original thing again. F of x equals 2x plus 1. Okay, but I know that I'm replacing x with something else. I'm replacing x with 3x, right? So that means that instead of x there, I'm writing 3x plus 1. Right, this purple thing has replaced the red thing. And so what I can write then is that f of 3x is equal to, well, I just do my multiplication here. This is going to be 6x plus 1. Done. Okay. Over here, we're still dealing with our function f, but now we're replacing it with this blue thing, x plus 3. All right, well, we can follow the same pattern, no problem, right? I'll start by writing out my, my normal form, the form that it gives me, where I've got this x here and here, but this just means that now I'm replacing that thing underlined with red with this thing underlined in blue. So wherever I found x in the equation, stop right here, right? An x, I'm about to write a x again. I have to replace it with that thing, x plus 3 plus 1. Okay, so I've replaced x with x plus 1. And that means that f of x plus 3, all I have to do is a little bit of distribution, right? Equals 2x plus 6 plus 1, or 2x plus 7. All right, so we got a bunch of tricks up our sleeves. Right, there you go. Okay, so there's 2 examples. What I want you to do, let's see, we're gonna have group A, B, and C. Okay, we're gonna have group A, B, and C. Group A, I want you to find f of, let's say, f of yeah, won't be, it's not too challenging. F of 3x. Group B, I want you to find f of x minus 7. And group C, I want you to find f of x over 2. All right. A, B, and C. I would say A is the easiest, B is the mediumest, and C is the most difficult. And so I'll split you up into groups. And for each of you, there's an extra challenge. If you finish that, I am introducing another function, which is h of x equals 2, let's change it. Let's make it 5x plus 3. And I want you to find f of h of x. Look at that. Ever seen anything like that before? I want you to find f of h of x. I have to take a screenshot of this, otherwise I will. You guys can do this too, because we're gonna go into breakout rooms, so you're gonna lose this. Take a screenshot or just remember it. There's a button I can press somewhere. Part of this. Save is a save. Screen save. Show in folder. Okay. All right. So, any special requests for which group you want to be in? You can type it in chat. I'm going to make some breakout rooms. We're going to have 3 breakout rooms. Created them automatically, and they just put you folks in the same order again. So we're going to do some exchanging. This one. Okay, I'll share this. Folks, just on this next slide, I wanted to talk briefly about calculus because honestly, sometimes in high school, we do all these pre-calculus classes, right? We're doing pre-calculus 11 and 12, and it doesn't really talk about what calculus is. So I just wanted to give you a little bit of an introduction to calculus, what it is, and what you do when you do calculus problems. So basic calculus is split into 2 big areas. First is finding derivatives, okay? Or basically it's finding the slope of any graph. This really is, like, we've done this work before, right? Can you tell me what the slope of this graph is? Slope is what? Can you tell me what the slope of this is? Oh, chat. Yeah, it's 3, exactly, right? We learned that we can just identify that there, and that tells us what the slope is. And that's easy, right? That's something like we can do there. If I graph this, we can look at any point and the slope is consistent. So we're going to be able to find the slope of that graph. What we challenge ourselves with in calculus class is to, like, let's say we've got now a more complex graph, this kind of teal colored one, and I'm maybe asked to find the slope at a given point, like this P for point here. We're kind of highlighting the slope as this pink color here, right? We can imagine that if we zoomed in, this will be the slope. Can you find the slope at that function, at that point? And we can with calculus. So let's just open up, this is, I believe, a Desmos graph, and there's lots here, right? So we can imagine maybe, is it gonna be this one? Yeah, see how I can trace along this curve, right? Maybe I stop right here, and if I zoom in, and zoom in, we can see it kind of flattens out, and it gives us a pretty good ability to estimate slope, right? I'm gonna zoom back out here. And that slope is gonna be something like along that line. You know what I mean? So we wanna try to find out what that slope is. And in fact, we wanna not just be able to find the slope there, but we wanna find the slope right here as well. We can see it's going to be different. We want to be able to find the slope here and here as well. It's going to be different. It's a slope that is changing. And so calculus, right, here's the slope. Calculus, finding derivatives, lets us find the slopes of that curved line at any given point, all right, and describes it as a function, basically, all right? So we can see how that slope is changing. It's a much more complex shape than just a straight line that we're used to, but we can be able to find the slope at any given point. This is kind of I didn't put this graph together, but this is a neat thing that helps us find the slope of it. All right. So that's the first area of calculus, finding the slope at any given point, right? On a function. The second part is finding integrals, or finding the area under a graph. So honestly, this is already something that we can do. Maybe we haven't thought about it too much, but if we had like some sort of graph, that looked like this, and we had to find the area from here to here, this is a pretty simple shape. We can split it up into two. We do this in physics. And we have a rectangle and a triangle. We know how to find areas of rectangles and triangles. We can find them and add them up. But if we have something more complex like this one, this function, and we're trying to find it between 2 points, right? Our area between A and B, that becomes more complex. How do we do that? I think we have another Desmos graph that kind of helps with that. So, or it illustrates it, right? So the challenge for this area of calculus is trying to find the area under a curve. And we can see how that area, this one is actually calculating it for us here, A equals something, right? It's certainly not an easy thing to figure out. It changes because of our curved shape here. We're not just dealing with regular shapes. So that's what we call finding integrals or integrating, trying to find the area under a graph. And so I've got a note here. We can already do these things with many simple graphs. Calculus gives us the skills to do it with almost any graph. All right, in calculus, you begin to learn and use many shortcut methods. Before you do, you learn some of the fundamentals. And I always give students a warning. When you start calculus class, you start with some of the hardest stuff, because you got to start with the understanding of it, like how it works and that kind of thing. And then you start to learn shortcuts, and you're able to do some of these complex questions real quick. There's an example in your textbook, example 6, that when I saw it, I'm like, hey, that's a calculus thing. It doesn't specify in your textbook that it's a calculus thing, but I thought it was kind of cute that they just threw it in there. So we're going to walk through that. Example 6 here showcases the difference quotient which is the first way many calculus students learn to find derivatives. So let me just write it out for you. It says if f of x equals 2x plus 1, it says find or determine f of x plus h minus f of x over h. So it's this kind of complex thing, right? It's this kind of complex thing. Many students, when they first begin calculus, will start doing this with like every equation. Okay, so let's try this, right? So we know what f of x is, and we have this big statement here, right? We have this big statement here, but let's kind of go bit by bit. We're going to start with this part, f of x plus h. Actually, I'll start highlighting instead. How about that? Okay, we're going to find this. All right, so there I'm finding f of x, except that we're finding f of x plus h. So this will be f of, this will become, this part highlighted in yellow, 2 times x plus h plus 1, right? So that's my part here. I'll try to track things nicely. That's my part highlighted in yellow here. We're subtracting from that just regular old f of x, right? So that's minus 2x plus 1, and it's over h. So let's just see if we can highlight to keep track of things, right? This orange bit here, this was just replaced with 2x plus 1, our normal function. Moving on from there, we see that we can do a little bit of distribution here, right? We end up with 2x plus 2h plus 1 minus 2x. Oh, and I forgot to keep this in brackets because that'll be important. We've got a minus sign, minus 1. That's all over h. Okay, and we see that some things cancel out. We've got a 2x minus a 2x, that's going to cancel out. We've got a 1 minus a 1, that's going to cancel out. That leaves us with 2h over h, right? Everything is canceled out on the top except for the 2h. We have the h on the bottom. This means that we can cancel out h. We're left with just 2. It's our final answer, right? After all that, we're left with just 2. I told you that at the very beginning, or that, calculus students often use this to begin doing calculus. In fact, they use it to begin doing differentiation or derivatives, finding derivatives. Finding derivatives finds the slope. What is the slope of this function here? We can see because it's in mx plus b form, so we focus on this. Evan's got it, right? The slope is 2. And if we follow our work here, at the very end, we got a value of 2. So this work, it's more complicated than just looking at that number, but we found our value 2, right? So this is a way of finding a derivative, differentiating. Okay, I'm going to take a poll. How from 0 to 5, how interesting was it to learn about calculus just there? 0 being that was the worst thing that I've ever learned about in my life. That's 0. 5 being that was very interesting. I'm so glad that Mr. Bohr took 15 minutes of our Math 10 class to learn about calculus. So Drayden says it was at 1 billion, and then said just kidding. Okay. All right, so we've got a couple people saying that was interesting. I'm glad that we spent some time learning that. Okay, some sort of middle of the road or closer to the bottom. All right, honestly, folks, to me, that's worth it. If a few of you have said, like, I enjoyed learning about it, or like it was something neat to learn about, I'm glad. I'm happy. It was worth it. Thank you. You won't be doing any calculus on your homework assignment. There it is. Let me just see that, because that looks like a lot of numbers, doesn't it? Let me see if we can eliminate some there. 2 to 4 ACE. Those will go pretty quick. Yeah, 9. Don't worry about 9. Okay, I'm canceling 9. 12A. That's good. 15. 15 brings back some memories. And 18. Yeah. Yeah, we'll do 15 and 18 as well. Okay. So we're eliminating 9. Don't do 9. Oh, hold on. There. So folks, we've got about 7 minutes of class left. We'll spend 7 more minutes here or so in class. If you do have any questions as you're going, let me know, but you can start your homework and then we'll be dismissed soon.